December 20th, 1940. A nondescript conference room in Washington, D.C. Representatives from Todd Shipyards Corporation and Bath Iron Works sat across from British shipbuilding surveyors who had crossed the Atlantic with a single desperate mission. The Battle of the Atlantic was devouring Britain's merchant fleet faster than shipyards could replace them. German U-boats were sinking cargo vessels at a rate that threatened to strangle the island nation completely. The British needed 60 merchant ships, and they needed them within months, not years. Seated at the end of the table was a 58-year-old man with silver hair and rimless spectacles who looked like a banker but spoke like a construction foreman. John Kaiser had built roads across California, concrete structures across the western states, and the monumental Hoover and Grand Coulee dams. What he had never built, in his entire life, was a single ship, not one vessel, not even a rowboat. Yet within 4 years, if you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. His name would become synonymous with a revolution in industrial production so complete that historians would call it the miracle that won the war. The British surveyors eyed Kaiser with skepticism barely concealed behind diplomatic courtesy. Traditional shipbuilding was a craft refined over centuries. Building a merchant vessel required anywhere from 6 months to a year, sometimes longer. Master shipwrights supervised teams of skilled workers who constructed each ship as a unique creation, one piece at a time. The idea that this dam builder from California could revolutionize an ancient industry seemed absurd on its face. Kaiser listened to the specifications. The British had brought blueprints for a simple 10,000-ton cargo freighter based on a late 19th century design. It was deliberately old-fashioned, powered by a triple-expansion steam engine that machine shops across America could manufacture without specialized knowledge. 5 cargo holds, a single-deck gun for minimal defense. Nothing sophisticated, nothing complicated. Just a basic workhorse capable of carrying tons of supplies across submarine-infested waters. The shipyard representatives from Todd and Bath discussed construction timelines using the traditional methods. 230 days per ship was the industry standard. Perhaps, with considerable effort, they could reduce that to 180 days. The British surveyors nodded. Even at that pace, 60 ships would take years to complete, time Britain did not have. Kaiser asked a question that changed everything. Why does it take that long? The shipyard men explained the traditional process patiently, as one might explain to a child. You laid the keel, then built upward from the bottom of the hull. Each plate was fitted individually by skilled workers. Riveters worked in teams, heating rivets until they glowed red-hot, then hammering them into place while another worker held a bucking bar on the opposite side. It required tremendous strength and years of training. Each ship was essentially handcrafted. Kaiser, who had spent 2 decades building massive construction projects ahead of schedule and under budget, saw the problem immediately. They were thinking about shipbuilding the way it had been done since the Phoenicians. They were building vertically, from the keel up, treating each vessel as a custom creation. What if instead you thought about it horizontally? What if you built a ship the way Henry Ford built automobiles? The concept was revolutionary, and it was met with immediate resistance. Ships were not automobiles. The stresses on a hull at sea were nothing like the stresses on a car on a road. The ocean was unforgiving. A single weak point could split a hull and send hundreds of men to the bottom. Shipbuilding could not be rushed, could not be simplified, could not be turned into an assembly line operation. The very suggestion revealed Kaiser's dangerous ignorance of basic marine engineering. But the British were desperate, and Kaiser was persuasive. He proposed a partnership. Todd Shipyards would provide expertise. Bath Iron Works would contribute technical knowledge. Kaiser would handle the innovation and mass production. Together, they would build 60 ships for Britain faster than any ships had ever been built before. On December 20th, 1940, the contract was signed. Todd Bath Iron Shipbuilding Corporation would build 30 ships at a new yard in South Portland, Maine. Todd California Shipbuilding Corporation, with Kaiser as the driving force, would build the other 30 at a location that did not yet exist, on empty land in Richmond, California, just across the bay from San Francisco. Kaiser had neither shipyard nor workforce. He had no cranes, no slipways, no fabrication shops, no trained shipbuilders. What he possessed was absolute confidence that traditional methods were inefficient, and that any process could be reimagined if you were willing to challenge every assumption that had ever been made. Construction of the Richmond shipyard began immediately in December 1940. Kaiser applied techniques he had perfected building dams. Instead of erecting one large facility and building ships sequentially, he designed multiple parallel shipways where vessels could be constructed simultaneously. He installed railroad tracks and overhead cranes in configurations that allowed materials to flow to workers rather than workers moving to materials. He borrowed ideas from automobile manufacturing, from aircraft production, from every industry that had ever figured out how to build complex machines quickly. Most radically, Kaiser decided to abandon the rivet entirely. Riveting had been the foundation of ship construction for a century. It was proven, reliable, understood, but it was also slow, labor-intensive, and required highly skilled workers. Each rivet had to be heated, positioned, and hammered into place by a team. A single Liberty ship required hundreds of thousands of rivets. Training a competent riveter took approximately 6 months of intensive work. Kaiser proposed using welding instead. Electric arc welding had existed since before World War I, but naval architects had avoided it for major structural applications. Welded joints were considered weaker than riveted ones. There were concerns about metal fatigue, about stress concentrations, about the long-term integrity of welded hulls subjected to the twisting forces of ocean swells. Traditional shipbuilders viewed welding as suitable for repairs or minor applications, but not for primary hull construction. But welding had one overwhelming advantage. It could be taught to a novice in approximately 2 weeks. Instead of requiring teams of strong men with years of training, a single worker with a welding torch and a few weeks of instruction could join steel plates as effectively as an experienced riveting crew. For Kaiser, trying to hire thousands of workers in a country about to enter a war that would draft millions of men into military service, this was the difference between success and failure. The decision to use welding was not Kaiser's alone. Associates who visited Ford Motor Company's River Rouge plant reported back on modern manufacturing techniques, including extensive use of welding in automobile production. Kaiser seized on this approach and expanded it systematically. If welding worked for cars, it would work for ships. The naval architects could complain all they wanted about unproven technology. The calendar did not care about tradition. The first keel for a British ocean-class cargo ship was laid at Richmond Shipyard No. 1 on April 14, 1941. Just 2 days later, on April 16, the United States Maritime Commission issued an urgent request. Kaiser needed to open a second Richmond shipyard immediately, operational by September, to build what were now being called Liberty ships for the American merchant marine. The British contract had been proof of concept. Now America wanted the same miracle for itself. Kaiser's response demonstrated the aggressive confidence that would define his entire wartime operation. He agreed to build Yard No. 2, even though Yard No. 1 was barely half finished. He agreed to have it operational in 5 months, even though conventional wisdom said building a shipyard took at least a year. And he agreed to production targets that experienced shipbuilders called impossible. He would build Liberty ships in less than half the time traditional yards required. The technique Kaiser pioneered was modular construction through extensive prefabrication. Instead of building each ship as a single integrated project from keel to superstructure, he broke the vessel into major subassemblies that could be constructed simultaneously in different locations. The bow section could be built in one shop, the stern in another, the deckhouse in a third. Entire bulkheads could be prefabricated with all piping and electrical wiring already installed. Then, using massive cranes, these prefabricated modules would be lifted into place and welded together on the shipway. This approach required a fundamental reorganization of how work was divided. Instead of skilled craftsmen who understood every aspect of ship construction, Kaiser created specialized stations where workers performed single, repetitive tasks. One worker might spend all day welding a particular type of joint. Another might only install specific pipe fittings. Another might only work on electrical conduits. No single worker needed to understand the complete ship. They only needed to master their specific operation. The parallel with Henry Ford's assembly line was obvious and intentional, but ships presented challenges automobiles did not. A Liberty ship was 441 feet long and 56 feet wide. It displaced 14,000 tons fully loaded. You could not build something that large on a moving assembly line. Instead, Kaiser created a stationary assembly process where materials and subassemblies moved to the ship via railroad cars and overhead cranes. The vessel stayed in place on the shipway while the factory flowed around it. Prefabrication also happened off-site. Machine shops and fabrication plants across the United States manufactured components to standardized specifications, then shipped them by rail to Richmond. Triple expansion steam engines arrived from the Joshua Hendy Iron Works in Sunnyvale, California, already tested and ready for installation. Deck houses arrived as complete units from steel fabricators in the Midwest. Even major sections of hull could be constructed at remote facilities and transported to the shipyard for final assembly. The scale of this operation required labor on a scale Richmond, California had never seen. In 1940, Richmond had been a quiet city of 20,000 residents. By 1944, over 100,000 people would be living there, most of them working in the shipyards. Kaiser recruited workers from across the United States, offering wages higher than comparable wartime industries and promising employment to anyone willing to learn. This created an immediate problem. The massive influx of workers overwhelmed Richmond's housing capacity. Families arrived to find nowhere to live. Kaiser's solution was characteristically direct. He built housing. Thousands of temporary housing units went up in weeks, creating instant neighborhoods. He constructed Atchison Village for white workers and later Harbor Gate for workers of all races. When even emergency housing proved insufficient, Kaiser purchased land across the Columbia River in Portland and built Vanport, which briefly became Oregon's second-largest city with 40,000 residents, all living in hastily constructed apartments designed to house shipyard workers. Then came an even more fundamental labor challenge. By late 1941, millions of American men were being drafted into military service. The pool of available male workers was shrinking rapidly, just as shipbuilding demands were exploding. Kaiser's response was to do something unprecedented in American industrial history, especially in heavy manufacturing. He hired women, not as secretaries or in auxiliary roles, but as welders, riveters, crane operators, and ship fitters. Eventually, 30% of the Kaiser shipyard workforce would be female. The cultural resistance to women performing heavy industrial labor was enormous in 1941. Shipyard work was considered too strenuous, too dangerous, too technically demanding for women. The welding itself required working in cramped spaces, sometimes suspended on scaffolding high above the deck, joining steel plates while wearing heavy protective gear. The physical demands seemed to preclude female workers entirely. But Kaiser discovered what the automobile industry had already learned. Welding did not require the same brute strength as riveting. A woman of average build could operate a welding torch as effectively as a large man, provided she had proper training and equipment. The 2-week training period meant women could be brought into production roles faster than traditional apprenticeships would ever allow. Kaiser did not hire women because he was progressive. He hired women because he needed workers, and women were available. The government created Wendy the Welder as a recruiting figure for the shipbuilding industry, attempting to replicate the success of Rosie the Riveter in aircraft manufacturing. Wendy never achieved Rosie's iconic status, but thousands of women responded to the call regardless of the propaganda. They came to Richmond, to Portland, to Kaiser's yards across the West Coast, and they learned to weld steel plates together to build ships that would carry American soldiers across 2 oceans. Kaiser also did something else unprecedented. He hired African Americans in large numbers and paid them the same wages as white workers performing the same jobs. This was revolutionary in 1942 America, particularly in a West Coast city experiencing massive demographic upheaval. Segregation was the norm, even in many northern and western cities. Black workers were typically confined to menial positions regardless of skill or qualification. Kaiser, who had no particular ideological commitment to racial equality, simply needed workers. He did not care about skin color. He cared whether someone could learn to weld, to operate a crane, to read blueprints, to install piping. Black workers at Kaiser's yards worked alongside white workers on the same projects, earning the same pay for the same labor classification. This did not mean racial prejudice disappeared. Tensions existed, but Kaiser's shipyards demonstrated that integrated workforces could be highly productive, a lesson that would resonate during the civil rights struggles of later decades. Kaiser recruited wounded veterans and workers with physical disabilities who had been rejected by other industries. If a man had one good arm and one good eye, Kaiser would find work he could perform. The elderly, who had been forced into retirement elsewhere, found employment in Kaiser's shops, doing tasks that required experience rather than physical strength. This created a workforce unlike anything American industry had seen. Housewives from the Midwest worked alongside farmers from the Dust Bowl, African Americans from the South, disabled veterans, elderly craftsmen, teenagers barely out of high school. Many had never seen an ocean before arriving in California. Few had any industrial experience. None had built ships. Kaiser's training programs had to start from absolute basics. The training was intensive but brief. Workers attended classes on welding techniques, on blueprint reading, on safety procedures. They practiced on scrap metal until instructors certified them as competent. Then they were assigned to production crews and began building ships. The philosophy was learn by doing. Mistakes happened. Welds were rejected and redone. But the volume of production meant workers gained experience rapidly, and second ships went together faster than first ships, third ships faster than second ships. Kaiser installed loudspeaker systems throughout all his facilities so he could address workers directly from his office. When production bottlenecks developed, he would get on the speaker and explain what needed to happen and why it mattered. His language was blunt, often profane, but somehow motivating rather than offensive. Workers called him Andy and meant it with a mixture of affection and respect. He created a culture where everyone understood they were not just building ships, they were winning a war. Motivational signs hung throughout the yards. The guy who relaxes is helping the Axis. Every rivet counts. Build it right, build it fast. Our boys' lives depend on you. The psychological pressure was enormous. Workers understood that the ship they were welding together would carry American soldiers into combat. A single defective weld could fail at sea, could sink the vessel, could kill dozens or hundreds of men. The quality control was intense, despite the speed of production. On September 27, 1941, the first Liberty ship, SS Patrick Henry, was launched at the Bethlehem Fairfield shipyard in Baltimore, Maryland. President Franklin Roosevelt attended the launch personally, delivering a speech that gave the ships their famous name. Referring to Patrick Henry's Revolutionary War cry, "Give me liberty or give me death," Roosevelt proclaimed that these vessels would bring liberty to the world. 14 ships were launched that day across multiple American shipyards in what was designated Liberty Fleet Day. The Patrick Henry had taken approximately 244 days from keel laying to launch. This was already faster than traditional construction methods, but still far too slow for the war effort's desperate needs. German U-boats were sinking Allied cargo vessels faster than America could build them. In 1942, American shipyards produced 11 million tons of shipping. German submarines sank 12 million tons. The Allies were losing the arithmetic. Kaiser understood the mathematics brutally clearly. Ships had to be built faster than submarines could sink them, or the war could not be won. Period. Every production technique, every innovation, every shortcut that maintained safety standards had to be implemented immediately. There was no time for extended testing, for cautious adoption of new methods, for gradual improvements. The shipyards had to achieve maximum production now, not next year. By September 1941, Richmond Shipyard No. 2 had its first keel laid for the Liberty ship SS James Otis. The yard, built in 5 months, was fully operational. It began with 6 shipways, expanded to 9, then to 12. Kaiser's yards were working 3 shifts, 24 hours per day, 7 days per week. Welding torches never stopped. Cranes never stopped moving. Workers poured in and out in constant rotation, but the ships themselves were under construction continuously. The first ships built using Kaiser's methods still took over 100 days from keel to launch. But the timeline dropped rapidly as workers gained experience and processes were refined. By mid-1942, Kaiser yards were completing Liberty ships in an average of 60 days. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By late 1942, the average had fallen to 42 days. By 1943, construction time had dropped to an average of just over 2 weeks. The speed seemed impossible to observers. Traditional shipbuilders insisted the quality must be suffering. Hulls built that quickly could not possibly be seaworthy. The welds must be weak. The structural integrity must be compromised. Kaiser was building disposable ships that would break apart in heavy seas. Critics predicted catastrophic failures. Some of those predictions proved tragically accurate, but not for the reasons critics expected. On January 16, 1943, the T-2 tanker SS Schenectady sat peacefully at dock in Portland, Oregon. The vessel had successfully completed sea trials just days earlier. The air temperature hovered around 39 degrees Fahrenheit. The water was nearly freezing. Without warning, and with a report that was heard for at least a mile, the deck and sides of the vessel fractured just aft of the bridge superstructure. The fracture extended almost instantaneously to the turn of the bilge, port, and starboard. The deck, side shell, longitudinal bulkhead, and bottom girders fractured. Only the bottom plating held. The vessel jackknifed. The center portion rose so that no water entered. The bow and stern settled into the silt of the river bottom. The ship had split completely in half while sitting at dock in calm water. The disaster sent shockwaves through the naval construction community. Here was proof that the critics had been right. Welded construction was fundamentally unsound. Kaiser's mass production methods were creating death traps. The all-welded hull had no ability to withstand stress. Traditional riveted construction would never have failed so catastrophically. Except the analysis was wrong. The problem was not welding itself. The problem was a combination of factors that no one had fully understood when Liberty ship construction began. The steel being used in Liberty ship hulls was ordinary mild steel, specified to be identical to steel used in riveted construction. In normal temperatures, this steel was ductile, meaning it could flex and absorb stress without cracking. But when cooled below a certain critical temperature, the same steel underwent a ductile to brittle transition. Below that temperature, the metal became brittle. Instead of bending under stress, it simply snapped. Traditional riveted construction had natural crack arresters built into the design. Rivets created joints where stress could dissipate. A crack propagating through a riveted hull would reach a riveted seam and stop, or at least slow down. The crack could not easily jump across the mechanical joint created by hundreds of individual rivets. Welded construction created continuous metal structures with no such natural barriers. A crack that started anywhere could propagate through the entire structure like lightning through a wire. The problem was compounded by design features no one had initially considered problematic. Liberty ships had square-cornered cargo hatches cut into the deck. Those square corners acted as stress concentration points where cracks could initiate. In traditional naval architecture, corners were rounded specifically to avoid stress concentrations. But rounding corners added manufacturing time and complexity. The Liberty ship design, optimized for speed of construction, used square corners. The welding process itself created additional problems. When steel is heated to welding temperature and then cools, the metal immediately adjacent to the weld undergoes structural changes. This heat-affected zone can become harder and more brittle than the surrounding metal. Inexperienced welders, rushing to meet production quotas, sometimes created welds with internal defects, microscopic cracks, or hydrogen embrittlement that weakened the joint. Most Liberty ships never experienced catastrophic failure. The vast majority served throughout the war without structural problems. but failures happened with disturbing frequency. The SS John P. Gaines broke completely in half in November 1943 while en route from Dutch Harbor in the Aleutian Islands to Seattle. Air temperatures hovered around 0 degrees Celsius. A large swell washed over the port bow. The ship fractured, presumably at the corners of cargo hatches, and the crack propagated straight through the plating, not along welds. The ship split in two. The bow sank. The stern drifted ashore in Alaska. 10 people died. Between 1942 and 1945, out of 2,710 Liberty ships built, approximately 19 experienced serious fractures that endangered or destroyed the vessel. Another 970 sustained fractures that required significant repairs. The rate of Class 1 casualties, those involving fractures that endangered the ship, was 4.3 per 100 ship years. This compared to approximately 1 per 100 ship years for conventionally built merchant vessels before the war. The United States Coast Guard established a board of investigation to determine what was happening and how to prevent it. The research led to fundamental advances in understanding how materials behave under stress, ultimately creating the field of fracture mechanics as a distinct engineering discipline. A British researcher named Constance Tipper at Cambridge University became one of the first people to fully document why the Liberty ships were breaking apart. She developed what became known as the Tipper test, measuring the temperature at which steel transitions from ductile to brittle behavior. Her research demonstrated that the steel used in Liberty ship hulls had a transition temperature between 15 and 65 degrees Celsius, with a mean around 40 degrees Celsius. This meant the steel was notch brittle during winter and spring operations in the North Atlantic, exactly when and where most Liberty ships were operating. Tipper's work proved that the failures were not caused by welding per se, but by the combination of brittle steel, stress concentrations from square corners, and operation in cold water. Traditional riveted ships had survived similar conditions because the riveted construction provided crack arresters, and because the stress of installation actually work-hardened the steel around rivets, making it more resistant to crack propagation. The solutions were implemented quickly once the problem was understood. Ship designs were modified to eliminate square corners on hatches. 4 riveted seams running the length of the hull were added as crack arresters in the welded construction. Welding procedures were tightened, with better training for welders and more rigorous inspection of completed welds. Most importantly, specifications for steel were changed to require better low-temperature toughness. The Charpy V-notch test, which measured absorbed energy during fracture, became standard for steel qualification. These modifications, implemented starting in late 1943, dramatically reduced failure rates. Ships built in 1944 and 1945 experienced far fewer structural problems than early production vessels, but the modifications slowed production slightly and added cost. Kaiser and the Maritime Commission had to balance safety against the desperate need for more ships immediately. The fundamental calculation remained brutal. Even with the structural failures, Liberty ships were winning the arithmetic of the Atlantic. By 1943, American shipyards produced 20 million tons of shipping. German submarines, despite their best efforts, could not sink that much tonnage. The Allies were now building ships faster than they could be destroyed. The production miracle Kaiser had promised was being realized, and it was turning the tide of the war. Kaiser's achievement becomes clear only when viewed at full scale. Between 1941 and 1945, American shipyards built 2,710 Liberty ships. 18 different yards contributed, but Kaiser's facilities were responsible for 1,552 vessels, over 56% of total production. Kaiser also built 50 Casablanca-class escort carriers, various auxiliary vessels, and hundreds of smaller craft. His yards produced approximately 30% of all vessels ordered by the United States Maritime Commission during the war. The peak of Kaiser's production came in 1943. His 7 shipyards, 4 in Richmond and 3 in the Pacific Northwest, were completing Liberty ships at an average rate of 1 ship every 42 days. At full capacity, the combined Kaiser yards were launching more than 700 vessels per year. At certain points, Richmond was launching ships faster than they could be named, creating a backlog at the Maritime Commission. The publicity stunt that captured public imagination came in November 1942. Kaiser Richmond Shipyard No. 2 decided to attempt building a Liberty ship in under 5 days. It was pure showmanship, designed to demonstrate American industrial capability and boost morale. The ship chosen was SS Robert E. Peary, named after the Arctic explorer and Bowdoin College graduate. The keel was laid on Sunday, November 8, 1942. Every shipyard worker understood this was special. Prefabricated sections had been prepared in advance, far more extensively than normal production. Work crews were organized with military precision. The absolute best workers were assigned to this ship. Every operation was choreographed. Materials flowed to the shipway in perfect sequence. Welders worked in relay teams. Cranes moved continuously. The work never stopped. 4 days and 15.5 hours later, on Thursday, November 12, 1942, SS Robert E. Peary slid down the ways into the water. The ship was not complete. Final fitting out would take additional weeks. But the hull was intact, the engines were installed, and the vessel could float. In less than 5 days, Kaiser's workers had assembled a 10,000-ton ocean-going cargo ship, thousands of individual components. The previous record had been 10 days for the Liberty ship Joseph N. Teal, built at Kaiser's Oregon Shipbuilding Corporation facility in Portland. The Peary shattered that record. No ship of comparable size had ever been built so quickly in human history. The story made newspapers across America. It became a symbol of American industrial might, proof that democracy and free enterprise could outproduce totalitarian regimes through sheer organizational genius and worker dedication. Critics pointed out, correctly, that the 5-day construction was not representative of normal production. It was a one-time publicity event using optimal conditions. The Peary had required months of advance preparation, gathering prefabricated components far beyond normal inventory. But the stunt served its purpose. It demonstrated what was theoretically possible with mass production techniques applied to shipbuilding, and it provided concrete evidence that American industrial capacity was overwhelming Axis production capabilities. Normal production, averaging 42 days per ship by 1943, was itself miraculous by any historical standard. Consider what that meant in practical terms. Every 6 weeks, another Liberty ship entered service. Every 6 weeks, another 10,000 tons of cargo capacity was added to the merchant fleet. Every 6 weeks, another vessel capable of carrying tanks, trucks, aircraft, ammunition, food, medical supplies, and thousands of other items needed to sustain armies overseas was delivered to the Maritime Commission. Multiply that across Kaiser's 7 shipyards, and the pattern becomes clear. Richmond alone was launching multiple ships per week at peak production. Add in the 15 other American shipyards building Liberty ships using Kaiser's methods, and the United States was launching approximately 3 Liberty ships every 2 days, averaged across the entire war. The strategic impact was decisive. Operation Torch, the Allied invasion of North Africa in November 1942, required moving 100,000 troops and their equipment across the Atlantic. Liberty ships carried the bulk of the cargo. D-Day, the Normandy invasion in June 1944, required even more massive logistics. Liberty ships delivered the supplies that kept Allied armies advancing across France and into Germany. In the Pacific, Liberty ships carried everything needed for the island-hopping campaign that drove across thousands of miles of ocean toward Japan. Liberty ships participated in every major convoy to Murmansk, the Soviet Arctic port that kept supplies flowing to the Eastern Front. These were the most dangerous runs of the war. German U-boats, surface raiders, and aircraft concentrated in the Arctic approaches. Convoy PQ 17 inches July 1942 lost 24 of 33 merchant ships, many of them Liberty ships, to German attacks. But the convoys kept running, and Liberty ships kept delivering cargo, because America could build ships faster than Germany could sink them. The ships served in other roles beyond cargo transport. Several were converted to troop ships, carrying soldiers across oceans. Some became rescue ships for convoy duty, equipped with additional medical facilities. Several were converted to aircraft transports, modified to carry fighter planes that were assembled and launched after arrival at forward bases. One Liberty ship, SS Stephen Hopkins, engaged and sank a German surface raider in September 1942 before being sunk itself, the only American merchant ship to sink a German warship in direct combat during the war. By war's end in August 1945, approximately 2,400 Liberty ships had survived. 310 had been lost to enemy action, mainly U-boat attacks and airstrikes. The survivors were surplus to peacetime needs. Most were placed in reserve fleets, mothballed in rivers and bays across America. Some served in the Korean War. A few remained in commercial service into the 1960s, but the vast majority were eventually scrapped. Today, only 2 Liberty ships survive as operational museum ships. SS Jeremiah O'Brien, built in 56 days at the New England Shipbuilding Corporation in South Portland, Maine, is moored in San Francisco. She participated in the Normandy invasion, making 11 round-trip voyages carrying cargo to the D-Day beaches. In 1994, she was restored to sailing condition and steamed back across the Atlantic to participate in the 50th anniversary commemoration of D-Day, the only large World War II vessel to make that return journey under her own power. SS John W. Brown, built at Bethlehem Fairfield Shipyard in Baltimore, is moored in Baltimore Harbor. She made 13 wartime voyages, including participation in the invasion of southern France in August 1944. Both ships are maintained by volunteer organizations and occasionally make short cruises to give modern Americans a chance to experience what it was like to sail in these vessels. One Victory ship also survives. SS Red Oak Victory, built at Kaiser Richmond Shipyard No. 3 in November 1944, is now a museum ship at the Rosie the Riveter, World War II Homefront National Historical Park in Richmond, California, on the site where she was built. The human cost of building Liberty ships at such incredible speed has never been fully calculated. Shipyard work was dangerous. Workers fell from scaffolding, were crushed by cranes, were electrocuted, were killed by falling steel plates. The exact casualty figures were never compiled comprehensively because each yard kept separate records and wartime censorship suppressed information about industrial accidents. But thousands of workers were injured, and hundreds died building these ships. The environmental cost was similarly never properly assessed. The massive industrial expansion left Richmond and Portland contaminated with heavy metals, chemical residues, and asbestos. Cleanup efforts continue decades later. The workers themselves, particularly those involved in welding and insulation work, were exposed to asbestos fibers and toxic fumes that would kill many of them decades after the war ended. Henry Kaiser's personal trajectory after the war illustrated both his genius and his limitations. He had proven that conventional wisdom about manufacturing could be challenged successfully. He had demonstrated that mass production techniques could be applied to industries that had always relied on traditional craftsmanship. He had shown that an outsider with fresh eyes could revolutionize an established field, but his success depended on wartime conditions that disappeared when peace came. Kaiser attempted to transition his industrial empire to peacetime production. He founded Kaiser Frazer Automobile Company in 1945, producing passenger cars and later the Kaiser Jeep. The vehicles were well designed and innovative, but could not compete against the big three Detroit automakers. Kaiser Frazer never achieved profitability and was eventually absorbed by American Motors. Kaiser Aluminum and Kaiser Steel were more successful, becoming major producers of industrial materials through the 1950s and 60s. But neither achieved the dominance in their industries that Kaiser had briefly held in shipbuilding. The magic combination of desperate need, unlimited government funding, and freedom to innovate without peacetime constraints could not be replicated. Kaiser Permanente, the health maintenance organization that grew from the medical clinics Kaiser established for shipyard workers, became his most enduring legacy. By providing prepaid medical care for workers and their families, Kaiser demonstrated that group health insurance could work at industrial scale. The model influenced American healthcare development for decades, though whether that influence was entirely positive remains debated. Henry Kaiser died on August 24, 1967, at age 85, in Honolulu, Hawaii. He had lived long enough to see a class of United States Navy Fleet replenishment oilers named after him, the Henry J. Kaiser class, commissioned in the 1980s. The lead ship, USNS Henry J. Kaiser, entered service in 1986. Kaiser never received the Medal of Honor or any military decoration. He was a civilian contractor, not a combatant. But President Roosevelt called him one of the men who won the war, and Dwight Eisenhower personally credited the shipbuilding program with making Allied victory possible. Without the Liberty ships, the entire Allied strategy would have been fundamentally different. The invasion of North Africa could not have happened in 1942. D-Day might have been delayed by years, if it had been possible at all. The Soviet Union might have collapsed without the supplies delivered through Murmansk and Persian Gulf ports. The Pacific Island hopping campaign would have been impossible without the logistics support Liberty ships provided. The lesson of the Liberty ship extends beyond World War II. It demonstrates what happens when necessity meets innovation without the constraints of peacetime conservatism. Traditional shipbuilding had evolved over centuries into a sophisticated craft. Experienced shipwrights understood every reason why vessels had to be built slowly, carefully, using proven methods. Every innovation Kaiser proposed had been tried before and rejected by experts who knew why it would not work. But Kaiser had one advantage the experts lacked. He did not know what was impossible. He looked at shipbuilding with fresh eyes, saw inefficiencies that had been accepted for generations, and asked why it had to be that way. When told it was impossible to build ships in weeks rather than months, he did not accept the answer. He found ways to make it work. The welding approach illustrates this perfectly. Naval architects knew welded construction created potential problems with brittle fracture. They were correct. Liberty ships did suffer catastrophic failures due to brittle fracture in cold water, but the alternative was not building enough ships quickly enough to win the war. Kaiser accepted the risk, built the ships anyway, and then worked to fix the problems as they appeared. The perfect became the enemy of the good enough to win. This philosophy carried risks that killed people. Ships broke apart at sea, sailors died. But more sailors would have died if the Atlantic had been lost to German U-boats because America could not build cargo vessels fast enough. The moral calculation was brutal but clear. Build ships fast, accept some failures, win the war. Or build ships slowly using perfect traditional methods, lose the Battle of the Atlantic, and watch Britain starve while Germany consolidated control of Europe. The structural failures that plagued early Liberty ships led directly to fundamental advances in materials science and fracture mechanics. Constance Tipper's work on ductile to brittle transition temperatures became foundational to modern metallurgy. The Charpy V-notch test, refined through Liberty ship failure analysis, remains standard for steel qualification today. Understanding how cracks propagate through welded structures influenced everything from bridge design to aircraft construction to oil pipelines. Modern welding codes, which specify preheating requirements and post-weld heat treatment for critical structures, trace their origins directly to Liberty ship failures. The concept of crack arresters in welded construction, now standard practice, was proven necessary by watching Liberty ships split in half. The entire field of fitness for service engineering, which evaluates how structures can continue operating safely even with known defects, emerged from trying to keep damaged Liberty ships in service during the war. The integration of women into heavy industrial work, though it did not survive the immediate post-war period, planted seeds that would grow decades later. The women who welded Liberty ships demonstrated that physical strength was not the only measure of industrial capability. Rosie the Riveter and Wendy the Welder became cultural icons precisely because they challenged assumptions about what women could accomplish. When women re-entered industrial work in large numbers during the 1960s and 70s, the precedent had been set. The racial integration of Kaiser's shipyards, similarly, provided evidence that integrated workforces could be highly productive. This did not end discrimination or solve racial inequality, but it demonstrated that the arguments for segregation based on supposed economic necessity were false. Black workers and white workers could labor side by side, earning equal pay for equal work, and build ships faster than any ships had been built before. The lesson influenced civil rights arguments in the 1950s and 60s. The Liberty Ship story is ultimately about what can be accomplished when crisis forces society to challenge every assumption that has ever been made. Traditional shipbuilding worked. It produced good ships using proven methods, but it was too slow for the war's demands. Kaiser's revolution worked, despite structural problems, despite quality control issues, despite every prediction that mass-produced ships would be death traps. The ships sailed, they delivered cargo, they won the war. 2,710 Liberty ships were built between 1941 and 1945. They carried millions of tons of cargo across 2 oceans. They sustained armies fighting from North Africa to Berlin, from Guadalcanal to Tokyo. They kept Britain supplied during the darkest years of the war. They delivered tanks and aircraft and ammunition and food, and medical supplies, and everything else needed to defeat fascism. The ships were ugly. Roosevelt himself called them dreadful-looking objects. They were slow, making only 11 knots maximum speed. They were uncomfortable, with crew quarters cramped and poorly ventilated. They were not sophisticated or elegant. They were simply functional, built to carry cargo and nothing else. But they were built in numbers that overwhelmed every obstacle. When German U-boats sank 20 Liberty ships in a month, American shipyards launched 60. When Japanese aircraft destroyed ships in Pearl Harbor, replacement vessels were already under construction. The arithmetic was simple and decisive. America could build faster than enemies could destroy. Henry Kaiser's insight was recognizing that speed of production mattered more than perfection of design. A good ship delivered today was worth more than a perfect ship delivered next year. The Liberty ship was good enough. It carried cargo from port to port. It survived most voyages. It won the war. What more could be asked? On the site of Kaiser Richmond Shipyard No. 3, where thousands of Liberty and Victory ships were built, stands the Rosie the Riveter World War II Home Front National Historical Park. Visitors can see the Red Oak Victory, one of the few surviving ships from that incredible production run. They can walk the decks, see the cargo holds, understand the scale of these vessels. They can read the stories of workers who built them, the sailors who sailed them, the strategic impact they had on the war. The story preserved there is not just about ships. It is about what happens when a society decides something must be done and commits fully to doing it. It is about challenging experts when necessity demands innovation. It is about accepting imperfect solutions rather than waiting for perfect ones that will arrive too late. It is about ordinary people accomplishing extraordinary things because the alternative was unacceptable. Kaiser's welding revolution made the Liberty ship possible. The decision to abandon rivets and use welded construction instead allowed thousands of unskilled workers to build ocean-going vessels in weeks rather than months. That single innovation, opposed by traditional shipbuilders, criticized as dangerous by naval architects, proven risky by catastrophic failures in cold water, nevertheless won the war. The trick was not insane, it was necessary, and necessity drove innovation faster than peacetime caution ever could. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.